Hey there. So in this video, we're going to take a look at some of the basics of an inference procedure called a one-prop z-test or a one-proportion z-test. So what that is, it is a test that we use to compare our observed sample proportion to a hypothetical population proportion. And that gives us evidence on whether our original hypothetical proportion was correct or not, essentially. Example that we last used in class was, let's say someone claims that they can make 80% of their free throws, and maybe we don't believe that they can make free throws that often. So we would have them shoot a bunch of free throws, see how many they made, and if they made a lot less than 80%, well, we would probably have evidence against their hypothetical proportion of 80%. But if they got, a sample rate pretty close to that 80%, we wouldn't really have evidence against them. If someone said, hey, I can shoot or make 80% of my free throws, if they went and shot 100 times and only made 60%, well, that's pretty far away from the 80% proportion that they claim to be. But if they say they can make 80% and they made 78% in a sample, well, that's not any evidence against them because that's pretty close to 80%. To calculate, how far away is far enough, we really need two things in this test. We need what's called a test statistic, which is a measure of how far our, from the hypothetical proportion, our sample proportion lies. And then from that, we calculate a p-value, which is what's the chance we would get a sample statistic at least as far away as the one that we got. If that's a low chance of occurring, strong evidence against the hypothetical claim. A large chance of occurring, not much evidence against that hypothetical claim. Now, no matter what type of significance test you're running, the test statistic will always follow this same sort of format or structure. Your test statistic will be equal to your statistic minus your parameter divided by the standard deviation of the statistic. Hopefully that structure looks a little bit familiar because that's essentially how a z-score is set up. A z-score, remember, is a measure of how many standard deviations away from the mean a value was. And that gave us a measure of how extreme or how average something was. And that's really what this is too. So an important thing to know here is that the statistic, that is what is observed. That's what we got from our sample. The parameter, that is hypothetical. And that comes from the null hypothesis of what we assume the parameter to be. The standard deviation of the statistic is the standard deviation of the sample distribution, and that'll either be, square root p times 1 minus p over n, or sigma over square root n, or s over square root n if we're working with means. We're going to get to means later on. But for proportions, your specific z-score or test statistic will be calculated like this. Your observed statistic, the proportion from your sample, is p hat minus the hypothetical parameter. That's the parameter that comes from your null hypothesis. So we're going to call that p0, meaning, h0 is the null, so p0 comes from the null. Divided by the standard deviation, we would use p times 1 minus p over n. Now the question here is, do we use p hat when we calculate the standard deviation? Do we use this p0? And remember that our decision on what to use was based on whether or not we knew the parameter. If we knew the parameter, we would use that here in the standard deviation. And only when we didn't know the parameter, we would use p hat in its place. In a significance test and our null hypothesis, we are acting as if we do know the parameter and we're assuming that it's p0. And so in this case, in a test, since we assume that to be true, we're using p0 here and here. Remember back when we did confidence intervals, we used p hat because in a confidence interval, we estimated the parameter, but we made no claim or no assumption about what it was. But in a test, a null hypothesis assumes that we know that parameter. All right, so that's how you're going to calculate your test statistic. And from that, you're going to be calculating what's called a p-value. And so let's take a look at an example of how to find the test statistic and the p-value. You'll need either your Inspire or 84, or you'll need table A to look up that p-value. Red doesn't really want to erase very well. Okay. No. So let's go back to the example of shooting free throws. Let's say that your friend claims that they can hit 80% of their free throws, but maybe we think that they're exaggerating and that truly the proportion is less than 80%. So our null hypothesis in that case would be that p equals 0.8, and the alternate would be that p is less than 0.8 because we think the true proportion is actually less. So let's say that you had them go down to the gym, they shot 100 free throws, and they made 72 of them. So they did make less than 80%, but we need to know what's the chance that an 80% shooter would have gotten 72 or less. Maybe that's just random chance, random variability is the reason they didn't, they made less than 80%. So to calculate your test statistic, well, we would calculate our z-score of p hat minus p0 over the square root of p0 times 1 minus p0 over n. And so our p hat would be 72 over 100, so that'll be 0.72 minus p0 comes from the null hypothesis, that's 0.8 over the square root of p times 1 minus p over n. So we're going to be using 0.8 since we are assuming that null to be true in this test. So 0.8 times 0.2 over 100. And that's going to give us a measure of just how far away from that assumed hypothetical parameter this 72% rate actually is. So I'm going to go on to an Inspire and figure out what that is. So 0.72 minus 0.8 divided by the square root of 0.8 times 0.2 over 100. I'm just setting it up just like that. Can you see that? There's a glare. I don't know. Well, there we go. And that turns out to be -2. So if they're really an 80% shooter, then this sample statistic is basically 2 standard deviations under the mean proportion that we would get if a person shot 100 free throws. And so that does seem to be a fair amount below average. But to get the chance of that, we need to calculate the p-value. So remember that there are really 3 different places you might get your p-value, depending on your alternate. If your proportion in the alternate said less than, then your p-value is going to be the area in the normal curve to the left of your z-score that you get. So you'll do normal CDF with those boundaries on the left side. If your alternate hypothesis says that p is greater than, then your p-value comes from the area to the right side, which actually in this case, since our p-value was negative, we'd have or our z-score was negative, we would have a huge p-value because it's everything to the right. And finally, if your alternate said that p was just not equal to, then we would have what's called a 2-sided test. And the p-value would be the sum of the 2 tails. So our z-score over here is -2, but we would also have one on the opposite side at +2, and the p-value would then be the sum of those 2 tails. Because our alternate said p is less than 0.8, we have what's called a left-sided 1-tailed test. And so how we'll calculate that is, well, one way is if you didn't have a calculator with you, you would go to table A, look up the z-score of -2, and follow it over. Well, actually, you wouldn't have to follow it over at all because it's -2.00. and look up your z-score there. Hopefully you've got an Inspire handy, and because we're using a z-score, we can use normal CDF. Later on, when we talk about means, you would use TCDF if your test statistic was a t-score. We're going to do that in the next section. So here we have a z-score and a normal curve for proportions. So we're going to go into good old menu 6.5 to normal CDF. Our lower boundary here would be -2. Or I'm sorry, our lower boundary would be -infinity. Our upper boundary would be -2. And then you're going to leave, because we've standardized it to a z-score, you're going to leave your standard deviation as 0 and 1. Let's see if we can get that on the screen. So that's what you're setting up right there. You're going to hit enter, and you're going to get a p-value of 0.0. There we go, 0.023. And that comes from the area of the left side of that normal curve. So if we were running this full test, this p-value would be less than our most common alpha level of 0.05. And so we would have strong evidence. We would reject this null hypothesis, and we would be able to accept our alternate hypothesis, because we do have strong evidence. You know, a person making 72 out of 100, that's pretty strong evidence that true proportion's less than 80%. All right, so there's an example of using the test statistic formula to get your test statistic or z-score value, and then using that to calculate your p-value, depending on the direction of your alternate hypothesis, greater than, less than, or not equal to. The very last thing that we'll talk about is checking conditions. We're going to get more into this and using this later on when we start, next video. We're going to run through the whole 4-step process. Just like confidence intervals, a significance test follows the full 4-step process: state, plan, calculate, conclude, or interpret. And one of those in step 2, you're going to go through the conditions. So these are the condition checks for a 1-prop z-tests. Fortunately, they're basically the same as they were for the 1-prop z-interval back when we calculated confidence intervals. First thing, you would need an SRS or a randomized experiment. An SRS would mean that we're taking our individuals randomly from the population of interest, and a randomized experiment would mean that we are randomly assigning to treatment groups. The reason that we are doing this, or the reason that this condition check needs to be met, is that's what allows us to know that we have an unbiased sample and that our estimate is unbiased. So that would center the sampling distribution at the true proportion. So knowing we have a random sample, that's what is letting us know that the mean of p hat is actually p, like it's supposed to be. The second condition would be your normal curve check. That would be that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And the same question comes up here. Do we use p hat? Do we use the parameter p? And because this is a test and we are assuming we know the parameter, that's what we're using. So n times p0 has to be at least 10. N times 1 minus p0 has to be at least 10. In that last example, we wouldn't take 100 times 0.72 from the sample. We would have checked 100 times 0.8, because that was the null hypothesis. Has to be at least 10, and it was. And also 100 times 0.2 has to be at least 10 as well. And then the last one is the 10% condition. So if you're sampling without replacement, then the population has to be at least 10 times your sample size. And if that's met, then you're good to go. In our last example, we wouldn't have really needed to check that because we didn't sample those free throws from a finite population. It's really an infinite population. Theoretically, that person could shoot an infinite number of free throws if they had enough time to do so. So those are your 3 condition checks for the one prop Z test. So a quick recap of what you should be able to do from this video is number 1, be able to calculate a test statistic using that test statistic formula. Number 2, calculate a p-value using your test statistic. And then number 3, be able to check the conditions or make sure those conditions are all met.